feature of the wave. Alright, now let's look at a simple sample example. If I were given a sinusoidal wave in this particular expression, 0.25 meters times sine of a phase angle, that phase angle is 0.60x plus 30t, where x is in meters and t is in seconds. Okay, this of course is the complete expression of the wave from which I can find everything I want. I can find amplitude, angular frequency, wave vector, the speed of the wave, the frequency of the wave, and the period of the wave, and so on. I can also find the velocity, Vy, of a particular oscillator on the wave at this location, x equal to 0.5 meters, and at that moment, t equal to 2.0 seconds. Okay, how would I find something like that? Well, simple. What you do is you compare this with the standard expression for the wave. Okay, the standard expression for this sinusoidal wave would be y, x and t, equals a sine kx minus omega t. Alright, that's the standard expression. Amplitude, wave vector, and angular frequency. Okay, immediately you notice there is a symbol difference, right? Here's plus, here's minus. What does that mean? What that means is that, remember I said you must have x minus vt, right? What if you have x plus vt? Well, that's allowed. That means v reverses the direction, okay? So v becomes negative effectively. That is a wave propagating backwards, that's all. So it is also possible for us to get a plus sign. All you realize this plus sign means that the wave propagates along the negative x direction, not the positive x direction. So that's all there is to it, to this positive sign. Okay, now if you compare the standard expression with what we have at hand, you find immediately, just by looking at the corresponding numbers, you find what is a equal to now? A is then equal to what? 0.25 meters, right? Okay, what about k and omega? Okay, k, just read that, okay? K equals 0.60. And what is the unit of k? It's 2 pi over lambda, right? So that's 1 over meter. So that's x is defined, is measured in meters, so that's 0.60 per meter. Okay, what about omega? What's omega equal to? Well, omega equals 30. And what is the unit? Well, the standard unit is radians per second, and t is indeed measured in seconds, so that's 30 radians per second. Alright, here is v, the speed of propagation of the wave. How did one find that? Now recall that v equals to, remember, k times v equals omega. So isn't it true that v equals omega over k then, if you solve for it? Okay, so you solve for it, you get 30 divided by 0.6. And that gives us 50 meters per second, okay? That's the speed of propagation of the wave, 50 meters per second. Okay, what's next? F and t. And how does one find that? Well, you know what omega is, right? So F is not equal to omega over 2 pi. Okay, so what you do, you take 30 radians per second. Okay, let's do that. 30 over 2 over pi. And we're getting 4.8 to 26 figures. 4.8 cycles per second, or 4.8 hertz. Okay, that is the frequency of the wave. And what about t then? Well, t is the reciprocal of f. Okay, so t is 1 over f. And what do we get? Okay, you invert that, you got 0.21 second. Okay, 0.21 second. So you see, by comparing this given form with the standard form, we can find all the parameters we're looking for. Okay, finally, how fast does a particle move at this location and this time? Well, what you're looking for is Vy, okay, which is partial y, partial t at that location x, right? Okay, let's do the partial derivative, shall we? Okay, y is equal to this, right? Let's plug that in here. Okay, so that is 0.25 meters. I copy that. Okay, and then you take a derivative of the sine function with respect to t, right? You find sine becomes cosine, but there's also 30 sticking out, so 30 radians per second. And what's left is a cosine function. Cosine. Okay, 0.6x. 0.6x. What's x? X equals 0.5 meters. Okay. I'm dropping out the units, but you know they're going to cancel out nicely. Okay, plus 30 times t. T is 2 seconds, 2.0. All right. One thing, be very careful about. What you're getting here, 0.6, that is 1 over meter. 0.5, okay, that is meter, so that is the dimensionless number. Okay, that dimensionless number, in fact, is 0.3. Now, is that 0.3 degrees or 0.3 radians? Okay, remember, if the angle is expressed in a dimensionless number, that by definition is radian, not degrees. So please make sure you set the mode of your calculator correctly. Okay, you must use radians, not the degree mode, otherwise you will get a wrong value of the cosine function. Okay, so make sure you set it correctly, and the rest is trivial. You just plug in the numbers into your calculator, and here comes the answer. Negative 6.1 meters per second. Now, what does that mean? It means an oscillator located at 0.5 meters away from the origin of x equal to 0. At that particular moment, 2 seconds into the oscillation, at that moment, this oscillator moves at a speed of 6.1 meters per second downwards. Okay, downwards means along the negative y direction. So that's how we find the speed. Of course, you want to find the acceleration, no problem, you take more derivative. You can also find the rate at which energy propagates along the string using the formula that we obtained before. So, again, everything is given from the expression for y as a function of x and t. You can solve for whatever you're looking for. Okay, let's look at another example, another sample problem. That actually is number 60 in the textbook on page 510. What we have here is a string, okay, of length L and linear mass density mu. The total mass of the string is small m. And at the end of the string is a mass of capital M suspended by the string. All right, what they're looking for is the time it takes for a wave to propagate from the bottom to the top of the string. So once you have a disturbance in the string, you know a wave is going to propagate upright until it reaches the end. The question is, how long does it take to do that? Okay, you know, if you want to find the time, then you got to know the speed and you know the distance, right? The distance is L. What about the speed? Well, the speed of the wave on the string, v, equals the square root of f over mu. F being the tension. There is one problem here, and that is the tension throughout the string is not uniform. If we can neglect the mass of the string from here to there, then of course the tension will be uniform, it will be equal to mg, right? Capital M times g. But the thing is, you cannot neglect the mass of the string. Okay, if you cannot do that, then the higher you go, the greater the tension, because, for example, this point must support all the weight underneath, including this part of the string. But that part will have to support even greater amount of weight, because that would include even this part of the string as well. So the higher you go, the greater the tension. So the speed of the wave is slower here and it gets progressively faster and faster and faster. We cannot use constant speed formula of distance over time, distance over speed to get the time. Okay, so how do we do that? Well, we must consider cutting the string into infinitesimal segments. Okay, this is x, and this is x plus dx. So look at the segment of length dx. I want to know how fast would it take, how long would it take for the wave to propagate over this distance dx from here to there. Okay, if that time is dt, if we know what that time dt is, then we integrate from here to there, we get a total time, right? So what is dt equal to? Well, dt is the time it takes to move for the wave to propagate a distance dx. dx equals v dt, right? Now that v is the speed of the wave at that location, which depends on the tension at that location, and tension varies. Okay, so v is not a constant, it depends on x, because it depends on the local tension. So let us find v first. V is the square root of f over mu. We need to find the tension here. So what is the tension here? The tension here is the force that has to support the weight of the block plus that part of the string. Okay, let us establish a coordinate system starting from the lower end of the string going upwards. The length between here and there, in other words, this is the segment of the string whose weight must be supported by the tension here. Okay, What is that mass of the segment? Well, if this length is x, okay, then the mass that has to be supported, let's call it m prime. Okay, what is that equal to? Isn't that equal to mu times x? Okay, linear mass density times x, right? Linear mass density is the total mass over the total length. Okay, times x. So that's m prime. The tension F at that location must support this weight plus that weight. Okay, so that's m, that's the block mass, plus m prime, that's the mass of the string from here to there, then multiply by g, you know? Okay, so the first term is a constant, second term is small m over length of the string times x, and then times g. That is the tension. You see, it's a function of x, right? Okay, what we do now is to plug that F into here, then we get V. Okay, plug that V into here, and we solve for dt. dt, the time it takes for the wave to go from here to there, is dx over V, which is the function of x itself. Alright, so what's that equal to now? dx over the square root of f over mu, the square root of f over mu. Here is f right here. This is f. Okay, capital M plus m over L x, and then times g. Right? So this is the time it takes to clear a distance of dx, for the wave to go up a distance dx. What is the total time it takes to go from here to there then? Well, that will have to be the integration of over dt, going from x equal to 0 to x equals L. Okay, so let's find the total time t, delta t, actually. That would be the integration over dt. The other side, you just integrate over dx, x going from 0 to L. So here is the integration. I'm going to take that square root of g out. It's a constant. 0 to L, right, the length, the other end of the string, dx, okay, big M plus small m over L times x. Alright, this integral, I trust that you can do it. The idea is I'm going to redefine a variable. Instead of x, I'm going to call capital M plus small m x over L. I'm going to call the whole thing, I'm going to call it u, okay? And then dx would be related to du, right? It's just a constant of m over L coming out. And so essentially the integral becomes some sort of constant time du over the square root of u, which is a simple power integral. It's u to the power negative 1/2 du. I trust that you can work it out, and you can verify that after you finish this integration, you will get the result given in problem number 60. It is 2 times the square root of L over mg, okay, L over mg, and then the square root of the sum of the two masses minus the square root of the mass of the block at the end. Alright, so this is how we find the time it takes to go for the wave to travel from here to there. And again, the key here is to realize that the wave speed varies. It actually increases as it propagates upward. So therefore you have to solve for dt equals dx over v, and you have to integrate. Alright, before we end the discussion of this problem, let's take a look at a particularly interesting special case, and that is if the hanging mass is 0. Okay, so all you have is just a free suspended string. If the capital M is 0, then you have just a square root of small m, which is the mass of the string, minus 0. And actually you notice that the square root of m and the square root of m cancels out. So what you're getting here is just 2 times the square root of L over g when m is set to 0. Okay. Now, what I want to know is, how does that make sense? It looks like not only is the big M gone, the mass of the block gone, but also gone is the mass of the string. It looks like the speed of the wave has nothing to do, okay, I'm sorry, the time it takes for the wave to go from top to bottom without the block, it has nothing to do with the mass of the string, no matter how heavy or how light it is, to take the same amount of time square root of 2 times square root of L over G. Okay, my question is, how come the mass of the string is gone from the equation? Why is it the time for the propagation of wave has nothing to do with the mass of the string? This is not just a mathematical consequence. I want to understand it physically. I want to understand the physical rhythm behind it. Okay, I propose to look at this from two angles. One is, you got to look at the dimension or the units. Okay, remember, we're looking for time t, right? It's got the unit of time, right? That's the time it takes for the wave to go from here to there. You know, the reason why there is a wave that can propagate is because there is a tension, right? Without a tension, the wave is not going to go anywhere. The speed will be zero, right? And the tension is because, you know, the string has to support its own weight. There's this gravitational effect. Therefore, it is clear that G must be part of the equation. Okay, G must be part of what determines delta T. And what about the length? Of course, the longer the string, the more time it requires to go up to the top. There's no question about that, right? So you know, delta T would be a function of L and G. That's for sure. Okay, both of these parameters will be part of the equation. And what about the mass, M? Mass M. You say, all right, I don't want to exclude the mass M, so therefore I have three parameters, L, G, and M. Now remember, I don't care how you combine these three parameters, the eventual outcome has to be some sort of time, delta T, right? And the question is, how does one combine these three parameters, L, M, and G, to get some sort of time? Well, this is an ancient problem. We learned that in the very first chapter of Physics 1A. Under what title? Well, remember two magic words, dimensional analysis? Remember that? Okay, at that time we learned that if you had a spring, simple pendulum, okay, which is basically a bar of mass m attached to the end of a string of length L, and the time t it takes for the string to swing back and forth once, which is the period, was given by the some sort of square root of L over G. And we learned that much later in Physics 1B as well, right? You know, that was a solution to the simple harmonic motion of the simple pendulum. Regardless of how we got it, we don't even need any knowledge of simple harmonic oscillation of the pendulum. All we need is to match the units of this side and that side, and invariably you're going to get some sort of constant. That could be 1, could be 2, could be pi, whatever, I don't care. It's just dimensionless constant times the square root of L over G. In other words, the mass m is nowhere to be found in that expression. Okay, so here's the first angle of looking at this problem. If you only have one mass, m, okay, one mass, m, then that mass has no place in your final expression for time, because the square root of L over G already gives you the correct unit for time. You stick mass anywhere into that equation, you're going to mess the units up. It won't be time anymore. Therefore, T and M does not belong. Okay, that's the analysis from units point of view. Of course, when you introduce another mass, you got two masses that you can deal with. Now, of course, you can have infinite possibilities. For example, you can introduce big mass over small mass. You can introduce small mass over big mass. You can introduce big mass squared over small mass squared, and so on. These are all dimensionless numbers, so you can stick them anywhere you want. Okay, so that's one consideration. Another consideration is the physical reasoning directly. That is, how come the mass doesn't matter? Now, what if I double the mass? Okay, I double the linear mass density rather. So I double the mass and keep the same length. What that means is the tension everywhere will be doubled, right? Everywhere the tension will be doubled. There's no question about that. Okay, because it has to support twice as much mass, of course. But don't forget, the linear mass density is also doubled, because that's what happens when you double the mass and keep L the same, right? So you double F, the tension, you double mu, which is the linear mass density. Don't you leave the speed as a constant? All right, that is why the mass of the string truly does not matter if there is no mass attached to the end. Okay, because it leaves the speed unchanged. So that's how we understand it.